Hello, everyone. Thank you for having me here at JScamp. I'm so grateful to be here. I must admit from the start that I'm crossing my fingers that none of my neighbors will start drilling or playing some loud music and that my intranet will remain stable. And talking about the intranet, I have a question to you. When was the last time you considered what actually happens right after you click on a web address? How long ago did you take that computer networking class? And would you like a refresher? Or for those lucky of you who never had to sit through the lectures and missed all the fun, would you like to learn it? I'm here to help you. You may ask yourself, why should you care? As engineers, most of us are on both sides of the story. On one hand, we are the ones who are responsible for setting up our web applications and creating a secure and efficient infrastructure for them. On the other hand, the rest of the time, we are in shoes of the users, relying on other engineers to care about our best interests to make experience fast and secure. That's why speed and security will be the central topics for us today. And after watching the talk, you'll understand better how we can improve speed and security of the application we develop and use. So grab your coffee and let's dive into what happens behind the scenes when you click on that link to check the weather forecast, pay your bills, or search for a kitten on the internet. My name is Olena. I'm a software engineer at Amazon Web Services. And in my free time, I'm excited about building and breaking stuff. I enjoy understanding how things work, from a dishwasher to the internet. I also love cats in all shapes and colors. So I thought, why not to combine these topics together for our story today? So we have a URL and we want to see a picture of a cute kitten. And honestly, let's admit, who doesn't? Let's start with a plan and outline the main steps on how we can reach our goal. With a URL in our hands, we'll start by searching for the web server to send the request. Next, we will talk about a common language for the communication. Then we will establish a reliable and secure connection, and finally download the image. And let's look at a very simplified illustration of the internet. We have our browser with the URL, and we have a server where the application with kittens is located. We don't know exactly where it is. It might be very, very far away. Our home router is located next to us and linked to the server by tons of routers, switches, cables. Overall, you know that the internet is pretty busy and messy place. We can divide it in two areas: local area network, all the stuff next to us in our control and care, and wide area network, where the rest of the World Wide Web is located. I suspect you won't be surprised if I tell you that the URL itself does not give enough information about the location of the server. The URL is just a friendly, readable reference to the server, but for the browser, it's still not enough. It's like I will tell you, let's meet in Starbucks. And unless you figure out the exact address, most probably I will be drinking coffee alone. What our browser needs is a specific address of the location where the server lives, some kind of coordinates. In other words, it needs an IP address. And in order to translate the URL into an IP address, we use domain name system, or DNS for short. It is like Yellow Pages, but decentralized and with extra features on top of it. So do you have to deal with DNS records in your day-to-day routine? Even if you don't have to manage DNS, I bet it still has an effect on your work, and understanding how it functions is helpful. So how does it work? Our browser will start by asking its neighbors for help, and I mean the network neighbors. The first door the browser will be knocking on is the name server of the internet service provider you are using or the DNS server of the organization you work at. There are several different types of DNS servers. For us at this moment, it is important that the DNS server we are talking to can send requests to other servers to get information on our behalf. That's why it is called DNS resolver, and we will call it resolver for short. What will resolver do? It will read the URL from right to left, beginning with the top level domain.com in our case. And we'll talk to one of the root name servers to find where the top level domain server is located. A root name server is like a village headman. He knows all the important people in the town. And by the way, a small interesting thing about the root name servers. You might be surprised that there are only 13 public IP addresses for all the root name servers around the whole world. It is because of the limitations in the original DNS specification, which was created years ago. In order to overcome this limitation today, we use Anycast routing to distribute the request across more than 600 different servers around the whole world. So the root name server will tell our resolver the address of the top level domain of the domain we are looking for. With this information, we'll move one step left, asking top level domain where to find second level domain. And finally, we'll get the IP address of the authoritative name server who knows the IP address of kttens and return this information back to the browser. Congratulations, we have the IP address. But that's not the whole story. Remember, I mentioned two things we particularly care about, speed and security. Let's talk about DNS speed first. It was a lot of work to find a single IP address, right? We want to avoid doing this repetitive long journey every single time we are connecting to a web server. That's where DNS caching comes into place. At all these stops, there is DNS caching helping to return the results faster. Moreover, your browser keeps its portion of cached DNS records, and if the website address is not there, then the resolver most probably has the information based on the internet activity done by other people near you. We know that caching is complicated. On one side, we want to save time and effort by retrieving data from the cache. On the other hand, as engineers, we want to be able to update the DNS records as fast as possible when needed. So the duration during which cache is stored is called TTL, or time to live, and we, engineers, are responsible for defining it for our DNS records. Have you ever run into a situation when you updated DNS records but couldn't access the website? Frustrating, right? In this situation, you can either flush the cache or, as alternative, set TTL to be short and wait till it expires. And in some DNS servers, the cache can't be flushed, so you will have to wait. Okay, that was about speed. What about security? To increase user privacy and security and prevent bad people eavesdropping and manipulating the data, we can use DNS over HTTPS. Compared to other protocols, this one is quite recent, but Firefox already switched to DNS over HTTPS by default for their users, at least in some locations. Another alternative is DNS over TLS, which was implemented separately. It uses a dedicated port 853, while DNS over HTTPS relies on 443, a port which we know is dedicated for HTTPS. Which one to use is up to the debate. I will leave more information about the standards at the end of the slide so you can decide what is better on your case. So now we have the address. How do we communicate with the server and ask for the picture? Remember this sophisticated and very detailed picture of the intranet I showed before? To make communication possible, all of these elements should understand and use same language to talk to each other. And as engineers, we call this language Intranet Protocol Suite, or TCP/IP. TCP/IP specifies how data should be packetized, addressed, transmitted, routed, and received. We can think of it in terms of layers. To explain it better, let's look how our browser will create a ledger to the server. By the way, if you attended computer networking class in the past, you might remember 7 layers from the conceptual model named OSI, or the Open Systems Interconnection. What we will cover today is a bit different, specific to TCP/IP, but you might find a close resemblance. So, at the center of our ledger to the server is the message itself, or what we want from the server. We want to get a picture of a cute kitten named Marcy. The content of this layer is called data and belongs to the topmost layer called application layer. Next comes the transport layer, describing the rules how exactly data will be transmitted. It takes the application layer, puts it into envelope, and adds a header indicating which protocol should be used. The options we have are TCP and UDP. And we will talk about TCP in particular a tiny bit later. Next, we indicate who sends the data. This is obviously important because the server will need to know where to send the reply. And who is recipient. And this is where the IP address we found earlier is useful. And this is network layer. Next layer contains MAC addresses. And finally, at the bottom, we have a physical layer defining the means of transmitting raw bits over cables. This ledger, or we can call it an envelope, will go through multiple hands until it reaches the server, where it will be opened layer by layer, starting from the bottom, checking to whom it was addressed, who sent it, which protocol should be used, and what the message is. The server will assemble a reply and send it back to the browser. What can we do to make this communication faster and more efficient? We can and we should be using HTTP2, the second major revision of Hypertext Transfer Protocol, which changes how the data is framed and transported between the client and the server. It is drastically different from the older version 1.1, and it allows making the communication faster, simpler, and more robust overall. HTTP2 introduces a binary framing layer, which can be seen as an extension to the application layer. This binary framing layer organizes messages into parallel streams of data and allows sending multiple requests over a single TCP connection without running into bottlenecks, as was the case for HTTP 1.1. On top of it, HTTP2 allows the server to push the content, meaning, for example, a client requests an index page. Once the page is received, the client may discover that it needs to fetch additional resources, such as CSS and JavaScript files. With HTTP2, the server will push these resources proactively while maintaining the separation between the pushed files and the initially requested ones. In HTTP 1.1, we relied on resource inlining for similar behavior, but it was causing larger HTML documents and longer load times. I will link an article at the end of the slides explaining in more details how HTTP2 works and how it improves the performance. As of 2021, around half of most popular websites rely on HTTP2. But if you are the owner of the one which still uses HTTP 1.1, it is time for a change. Great. So we know where the server is located and how to communicate with it. But how do we get data reliably? To deliver the message, server will divide the content into smaller chunks and send them one by one. The client, our browser, will catch the packages, combine them, and present to the user. And here is the challenge. While on the road, many things can go wrong. Some of the segments will get lost, corrupted, duplicated, and get out of order, messing up the message to the client. And the result might become unreadable and unrecognizable. We don't want to risk breaking our kitten or any other files, right? What should we do? Remember that I said we'll talk about TCP. That's what we will be using to solve this problem. We will employ Transmission Control Protocol, or TCP for short. TCP guarantees that the segments received by the client are the same as they were sent by the server. And to achieve this, every segment is numbered. This helps the client in two ways. First, to notice any missing segments, and second, to put received segments into the correct order. The client will confirm reception of the segments and will notify the server if any data is missing. By the way, the numbering does not have to start with 0. Rather, we begin at some random value suggested by the server during the initial introduction. And the introduction process is called a three-way handshake when 3 messages are exchanged to start a connection. Now we introduced ourselves to the web server and established a reliable connection. But there is one more thing about the internet. Not only it is not stable, it is also not safe. In reality, it is a dangerous place where many bad things can happen to our poor kitten or our banking details. Therefore, the question, how do we make the connection between the server and the browser secure? In particular, we care about 3 things. Confidentiality, that no one else can read the data we exchange. Authenticity, that we can have a certainty of who we are connecting to. And integrity, that no one tampers with the data, and if they do, we can recognize this and take an action. So we deeply care about these topics as users, but even more as engineers. So what should we do here? The way to protect the data is to encrypt it. In this way, for the onlooker, who intercepted the message, the message looks like a gibberish. And you're probably familiar with 2 ways of cryptography algorithms, symmetric and asymmetric. We'll come to asymmetric one a bit later, but first let's look how we can use an asymmetric cryptography to send a confidential message from our browser to the server. Server has a pair of keys, a public key, which may be known to others, and a private one, which is kept as a secret. These keys are unique. They are different from each other, but mathematically they are related. The public key can be freely shared on the internet. It is not a secret, doesn't have to be protected in any way. Anyone can have it. You, me, the browser. The private key is on the opposite, kept in a secure place and should never be shared with others. So our browser takes the public key from the server and uses it to encrypt the message. Then it sends this message to the server. Anything encrypted with the public key cannot be decrypted with the same key. It can only be decrypted with the corresponding private key, which the server keeps as a secret. So the server uses the secret key to decrypt the message that was sent from the client. And this is how the confidentiality of our message to the server can be protected. Those who intercept the message cannot decrypt it because they don't have the server's private key. And this is why it is so essential to keep the private keys secure and never share them with others. But there is a weakness here. Have you spotted it? How do we know that the public key we use does indeed belong to the server we addressed our message to? Someone could have pretended to be a kitten's server, while in reality all they want is to steal the data we send to kittens. To prevent this from happening, we need a mechanism to validate the identity of the server we are connecting to. Something like a passport issued by an authority we trust and having a mechanism to validate it quickly anytime. In realms of intranet, the passport is represented by a digital certificate and a digital signature, which are managed by the public key infrastructure. How does it work? The owner of the server will go to certificate authority to get a certificate for cute kittens. It will be verified by registration authority that this person is allowed to request a certificate for this website. Certificate authority works with software manufacturers, Google, Mozilla, Microsoft, to embed their certificates into the web browsers. Together, they are part of the public key infrastructure, which is responsible for creating, distributing, storing, and revoking digital certificates. So please take care of your website certificates. For the privacy of the users, we must keep them secure and up to date. But let's get back to the encryption topic. Asymmetric encryption has one big disadvantage. It is too slow to be used for encryption of all the data exchanged between the client and the server. How do we make it faster? We use symmetric encryption. In symmetric encryption, we need a single key, and to create this key, we rely on digital certificates, signatures, and a bunch of other procedures and algorithms. And here I'm talking in particular about TLS, or Transport Layer Security Protocol, which is used by HTTPS to establish a safe, encrypted connection and create a symmetric key with the help of asymmetric encryption. Talking about TLS, we must mention Cipher suites. A Cipher suite is a set of algorithms that help secure a network connection. For every website that uses HTTPS, as a user, you can see what Cipher suite is used. For example, these are security details for my connection with google.com, taken from Firefox. And the underlined line is an example of a Cipher suite. Cryptographic algorithms and parameters are broken or weakened over time. That's why not all Cipher suites are equally strong. In fact, when you think of it, we are in a constant race between creation of more powerful computers that can break cryptographic algorithms and invention of more advanced algorithms which can't be broken yet. That's why it is important to use algorithms which were not compromised yet. We must remember that a Cipher suite is as secure as the algorithms that it contains. Transport Layers Security Protocol plays a critical role in enabling privacy and data security for communications over intranet. The protocol evolved over the last 3 decades, and two latest and most commonly used specifications are TLS 1.2 and TLS 1.3. If you are using anything less than TLS 1.2, then your application and your users are vulnerable for attacks. Previous versions are deprecated and insecure. TLS 1.2 was defined back in August 2008 and is by far the most commonly used TLS protocol in the internet. Is it the best choice? Not anymore. TLS 1.2 still can be secure as long as you use specific configurations and cipher suites. However, TLS 1.2 supports an enormous amount of options, both secure and insecure, which makes configuration difficult and can lead to misconfigurations and vulnerabilities for attacks. And what can be worse than lack of security is the feeling of false security. TLS 1.3 attempts to help with this problem by dropping support for many insecure or obsolete features and removing support for weak and less used elliptic curves and cryptographic hash functions. It enables best practices, or it enforces best practices for popular encryption algorithms. In addition to security, TLS 1.3 improves the speed of handshake by reducing it from 2 round trips to only 1. Think of it, now our browser and the server can agree on a symmetric encryption key within just 1 round of communication. Isn't it impressive? It also allows using cryptographic material obtained in previous connections to improve load times. This is called zero round trip. Is TLS 1.3 perfect? No, but it accumulates learnings from previous protocols and is a step in the right direction to ensure security and privacy of the connection. But let's get back to our kitten Marcy. Now that we have a stable and secure connection with the server, it is finally the time to send the kitten to the browser. Congratulations, our mission is accomplished. And that was a long journey. Let's summarize what we have done. With the help of DNS, we have found the location of the server. We considered usage of DNS over HTTPS and DNS over TLS to hide certain aspects of DNS lookup. We agreed on using TCP/IP for communication rules between the browser and the server and discussed how TCP protocol helps keeping a stable and reliable connection. Then we verified identity of the server we are talking to and with the help of TLS created a symmetric key to efficiently encrypt the message. All of this and even more to transport the kitten. And this is just the tip of the iceberg. I would like to conclude this talk and leave you with a couple of useful links to check deeper the topics we discussed. I will share those links later in the chat. With that, thank you so much for watching. I hope that together we can, that I didn't mean to click on this. I'm sorry. What I meant is to show you this message, that together we can make the internet a safer and more secure place. Thank you so much.